Hi, my name is Chris Gomez, and I'm the director of the laboratory of SCABO at Kobe University, which is Sediment Hazards and Disaster Risk. And this is a poster I've done with my colleague Balazs Bralak from the ExoOcean Laboratory. So what I'm going to do is to walk you through this poster, which is named Morphological and Subsurface Evolution of a Coastal Beach in Sendai in Japan in the aftermath of the 2011 earthquake and tsunami. So let's zoom a bit on it. Where are we? So Sendai is here on the east coast of Japan, facing the Pacific Ocean. And that's unfortunately where the earthquake threw a series of tsunami waves to the coastal of Japan in 2011. And one of the areas that was impacted is the area here on the Sendai coast that we are going to look at. And that's the survey location. So this is the port, the brand new, at least dug out port. And we are just between this river, the Monakagawa, and the port here. And that's the survey location. So now if I move a bit back in time, so in 1947, that's before the port is there. So this is the state of the morphology of the coast at that time. And you can see the north, the shoreline of the sandy shoreline, the sand coast continuing right to the north. And this is the place where we stand. And then we move to 1967, and then you can see the port that has been built. And you can see also that they have been building a wall here, so that the spit here is not really connected or working so well anymore. And you have interconnection with the different fields that we have at the back. And the population has been also sprawling. You can see here on the image the inhabitation that were still actually not there yet in 1947. So population has been moving towards the sea, which is one of the issues as well. And then here we are in 2006, still looking at our area, survey area. You can see that sand has been dug out in these areas. There is a lot of work that has been done and reworked. But Takadai, a place which is a bit higher, has been created as well. So a lot of man-made features. But the area we're interested in here is still quite, in some ways, not pristine, but comparatively, it's still being reworked by natural processes. And then we go to 2011, and 2011, you can see that all shoreline is totally disrupted. The sand was pushed back into these areas here as well. And that's when we start looking at the geomorphology. So the geomorphology in 2011, you can see the sea has invaded towards the coastline, and then the shore here is only now a narrow strip of what it used to be. And one of the questions we have is like, okay, so that's what happened in 2011. What is the state of recovery, or how did it change over time? So what we did is we combined a UAV drone survey with using an iPad, simple, very laser SLAM survey, and mapping the two together. Now, one of the reasons for that is that the SLAM survey is not super accurate. It doesn't have a millimeter scale laser type of data set created, but this being said, it's still consistent in its creation. So what we try to do is to map the SFM-based data with this one to try to see whether we could match the two and limit the error. The result is actually not that bad. When you look at the variation and the error, we have an error which is less than about 20 centimeters between the two before we even match them. And then matching the two together afterwards, we could reduce that error. So why did we do that? I was not so, or we were not so interested in the morphology itself. For the sake of the morphology, what we wanted to see is to use that to look at what was inside the shoreline. And to see what's inside, it means that we used a GPR. So this is the GPR we used with an 800 megahertz shielded antenna. This is what you can see here. And we are dragging this on the ground. There is a wheel at the back. That's the coding wheel. The coding wheel is recording the distance. So you know when you send pulse, the radar pulse into the ground, where on your transect you are. So that's going to be a 2D. There is no GPS on that, but we have a start point and end point, and we go straight, basically. It's quite easy on the shoreline. And this is the GPR itself that creates the signal and all that, and connects back to a computer. And this is the computer we used actually to control the whole system here. It can be a tablet, can be other things, but I use a rugged laptop. It's often a bit better in the sense that it's quite sturdy. And then once we get this, what do we need to do? Well, I need this. Once we get this, what do we need to do? So we get the radar data that will look something like this. And you see that with this large band on top. So we don't want to see that because this is the signal traveling through the antenna and towards the ground, and the ground is just at this white and black delineation. So we get rid of this, and then once we have done that, we have actually a lot of the depth of the data is a lot of data. So what we need to do is to actually trim the mean energy of the data. So we get the mean of all those data set, and we get rid of it. We get this here. And then once we have this, we still have, you see those ringing effects that we have, which are horizontal bands related to the signal entering the ground first time. So we want to get rid of that because it's actually falsely emphasizing some features and modifying the signal. And because they are all parallel to the ground, we just need to have a filter that gets rid of everything which is parallel all at once. And we're going to do that using by subtracting the mean, the temporal mean of the signal. And then we get something which looks like this. And then once we are here, one thing we want to do is to see whether we can amplify the signal at the bottom. So when the signal, meaning the electromagnetic wave, is traveling through the ground. So one thing, we are not recording the electromagnetic signal. We record the electrical part of the electromagnetic signal in the GPR. But still, we are losing energy while it's traveling to the ground up to, we cannot actually, we don't have any energy anymore. So that's energy loss that we have with the depth. We want to compensate that and see whether we can see features a bit lower. And for that, we can use an energy decay, or we can play with the gain, and we get something which looks like this here. And then the last step is what you want to do is to make sure that what you're seeing on the graph here, I only added the time. This is the time window in nanoseconds. Or horizontally, we can see the distance. You want to convert that time into depth. And to do that, you need to have a model, which is a time depth model. And to do that, we're going to use the hyperbola. So like features like this, you see like a hat. So how do we use it? So we know how far we're traveling horizontally, right? And the depth is not actually the real depth. It's representing the time it takes for the signal to go in and out. So let's say we have an object which is reflective, and the antenna is right there. So we have the time between the two, so it's going to look down on the signal. We're going to have the object looking very deep because we're far away from it. And then the closer we get to it, the closer the object is going to look like. We're just getting closer to it. And the slope of that, because we are not in depth but in time, it's going to give us a relation between the horizontal movement and the time it takes to get down there. So using that relation, we can then back calculate the velocity of the signal in the medium. And then we use a lot of those, and we construct a time depth model, which is going to help us then reshape the signal. Here in a sandy signal, it's not too complicated because there is one or two velocities together. One would be to the saturated to semi-saturated area just underneath at the shore. And then you have the sandy part, which is like dry to semi-saturated, which is going to show a different velocity. And using that, then we can recreate the right shape of the different layers underneath. So what did we find? So first, we need also to add the topography. So and to do that, we used the SFM generated model added to the SLAM generated model. And this is what we did. Well, it's not that bad. And you can see the different geomorphological features. And those small dome-like here that you can see that you're wondering what they are, it's actually vegetation which is there, which is capturing the sand. So they look like these small things. And at the back, what we can found also quite a lot are debris from the tsunami. So cars and car bodies still being there, like being rusting for a couple of years already. And then when we go to the results, or at least let's look at this first printlet. Here, we can see that we have actually layers that are upon one another, like this one here, and this one here. So those are the backshore fill. So the sediments have been brought back by the sea, pushed back, and then filling up the hole that was created post-tsunami. And in this area where the sediment also, at least in this area, that was still there. The sediment where had been eroded, then they were placed back also with a typical shoreline process on top of that, I would say, ridge of what was remaining. It's not a ridge, what was remaining of post-tsunami. Then when we go and look sideways, then we can see the processes in the same way. The only thing is that we can see that the process is not only 1D when the sediment is moving from the sea towards land, it has also been spread in and out. And those are the things that we see. The other element that is important is the fact that we have a lot of punctual elements. So we are with an 800 megahertz antenna. So in that environment with a 0.0315 meter per nanosecond velocity, we are looking at elements that are a few centimeters in diameter being represented by hyperbola already. So we don't need to have like a huge block or huge deposit, but we have a lot of different materials which are actually located in this outcrop. And in this one, it's the same. We have a lot of small elements. So when you have those infill of sediments, you would expect to have actually like more sand-like material only, but it's not the case actually. You also have a lot of different elements. Now, one of the difficulties to interpret and understand is that on the shore itself, there is a lot of debris. There's even wood debris, like driftwood. So is it driftwood which is trapped in the sand, or is it just something totally different? This is hard to tell. But at least there is a lot of foreign or non-sand objects trapped in the reconstruction of this shoreline. And this is what we found doing this investigation. We have more GPR transect on the rest of the shore, but that's for another time. At least for startup, those are our preliminary results. So if you want to talk to me, you can see me how I look like here. So you should be able to find me on the JPGU somewhere around the posters or at the sessions. I will be at this session especially for instance, where I'm co-convening with Yuichi Hayakawa. And I hope you enjoy the JPGU and your time there.